All right, yeah, I think it does, right? Does it? Does it? Sounds like it.
Our next speaker is David Reutter from University of Hamburg, who's going to tell us about homotopy quantum groups. Take it away.
Yeah, first of all, thank you for the invitation. It's really nice to be here. And I'm a mathematician. It's cool to be here and to learn new things. And what I want to talk about is homotopy quantum groups. This is based on joint work in progress with Theo Johnson-Freight. And the idea, I mean, this really is sort of a side product of a project we're working on. And somehow what we'll see and what I try to explain in the next half an hour is how you can extract, for example, a bunch of just groups, like actual finite groups, from non-invertible symmetries in 4 and higher dimensions. That's one of the side products. And these we call these homotopy quantum groups. Okay, so let me sort of start with some motivation and let me look at a particular model of topological quantum field theory, namely these finite sigma models. This is essentially a sigma model, but everything is finite, so I can do my path integrals by just summing stuff up. This is a model we mathematicians like because we can make lots of conclusions about this. So I start with a finite topological space. Finite here means that all the homotopy groups are finite and there are only finitely many non-zero homotopy groups. And I can form a d plus 1 dimensional TGFT for any d, which assigns to a closed d manifold sigma. It just assigns pi 0 of the space of maps from sigma to x, and then you linearize it. And to a closed d plus 1 manifold, it assigns the sum over all homotopy classes of maps from m to x, and then you have some normalization. So you should really think of this as a sigma model, but where all integrals are replaced by sums. And I didn't tell you what you do to a d plus 1 dimensional Bordesen, but you can imagine it. You can sort of fix boundary conditions. Okay. So these are sigma models. Good examples are finite gauge theory for a finite group G, but you can also do higher form gauge theory. Here the R should be an R minus 1. I messed that up. So these sort of fit into this. And so in general, you can think of these as just sort of finite gauge theory for arbitrary higher forms and sort of mixed higher form things, if you like. Okay, fine. And something that's also, of course, very well known is that there exist dualities. So even if X might not be homeomorphic, it might not even be homotopy equivalent to Y, and still these sigma models agree, of course, and these are very interesting, these dualities. But these sigma models have more structure. If you look at them, this is not just a TQFT, in fact, it has a boundary theory. And the boundary theory that I'm going to use is a so-called Neumann boundary theory, meaning you basically just don't impose any boundary conditions. These are all discrete theories. We don't have to impose conditions on derivatives. There's just no boundary condition to do a Neumann boundary theory. So for example, I mean, you can just see it because these formulas here, I don't need sigma to be a closed manifold. It still makes sense if this is a manifold with boundary. And similarly, this M doesn't need to be a closed manifold. It can be a manifold with boundary. So this points to this additional boundary condition, which is sort of the empty boundary condition. And let's also remember this boundary condition. And the key statement is that while these sigma models can be isomorphic, these isomorphisms will permute the boundary theories. And in fact, if the higher homotopy, so I don't see the very high homotopy groups of my space X, but if those are 0, then I can actually recover my space X from the pair of the TQFT and the boundary condition. And whenever something like this happens in mathematics, what you would say is, well, okay, then spaces, or at least these spaces which have sort of only low-dimensional homotopy groups, they are sort of a subclass of these pairs of TQFT and a boundary theory. So what I should now do is I should just pretend such a thing is a generalized space, and I should do everything I've done with spaces for pairs of a TQFT and a boundary theory. And I should sort of counter-check the things that I've done by sort of comparing them to what happened in the case that this is a sigma model with its Neumann boundary theory. So why do we care about such things? Well, we care about such things because they appear as symmetries, as non-invertible symmetries of QFTs, which we've already seen this week a bunch of times. A pair of a TQFT and a boundary theory, let me sort of use, I mean, the SymTFT paradigm we've seen is much older, but let me use the formalism of Fried-Moore-Telemann. Such a pair describes precisely the symmetries, the non-invertible symmetries of a d-dimensional QFT. And I won't mention how they call them, but here's a picture.
Your question, how do you recover the dimension?
How do I determine which dimension? Up here?
Yeah, so...
Yeah, there's a parameter. Okay. So for every d, I can do this. Okay, you could say a pair for fixed d is like a space which has only homotopy up to level d. Okay, fine. So now let's take this perspective, right? If I want to say such a pair is like a space, and sort of the space of symmetries of a d-dimensional QFT, what I should do the things with it that I do with spaces. And the first thing I do with a topological space is construct basic invariants. And the most basic invariants are the homotopy groups. So what is this? It's a fundamental group, or rather a fundamental groupoid. I can have many different base points. It doesn't need to be a connected space. And I have the higher homotopy abelian groups. And of course, those aren't just abelian groups. Those are for every base point in X. I do have such a group, and I have an action of pi1 on these groups. And the way to package this information is to say this is a functor from the fundamental groupoid to the category of abelian groups. That's sort of the cleanest way to package it. It's a local system in mathematics terms. And so let me remind now, let me sort of say a d-dimensional quantum space is a pair of a TGFT and a boundary theory. I'm not yet convinced this is really the way one should say it, so I'll just say it for this talk, but this is really the mindset I want you to have. And for the mathematicians or the sort of mathematically minded people in the audience, let me sort of refine this a little bit, the way we model such a pair. The way we model it in this project is as follows, but you can really sort of just think of it as a pair of TGFT and boundary theory. The way we model it is we work with a once extended, so you also assign categories to codimension 2 manifolds. Open closed, so this means it's defined on manifolds with boundary. This encodes the fact that you have a boundary theory. We just work framedly, that's sort of from a mathematical perspective just the most general collection of things you can do. And we consider not necessarily compact d plus one-dimensional TGFT. So compact d plus one-dimensional TGFT here means it's defined on all top-dimensional Bordesons. That gives me linear maps and numbers for all Bordesons. But we're dropping this condition, meaning we don't want to have linear maps. We don't need to assign linear maps to all Bordesons, so we just sort of remove some of the finiteness conditions that TGFTs impose and sort of make it more general. We only need linear maps to Bordesons that have outgoing boundary non-empty, and this usually brings in all these sort of slightly non-finite, slightly less semi-simple examples as well. Okay, and here's a preview of the theorem that I want to explain a little bit. If I am in dimension 4 or higher, so this is sort of the symmetries of a 4 or higher dimensional QFT, and if I have such a quantum space, and I assume it's compact, so this is sort of the strong finiteness conditions that I can really define it on all 4 and 5, sort of 5 manifolds with boundary, I get a linear map. And it's superlinear, so meaning it's valued in the sort of in superlinear categories, functors, natural transformations. Then I can extract from this data a finite groupoid, and for every 2 up to d minus 2 finite abelian groups with an action by and every base point a finite abelian group with an action by pi1. This is just something that I can extract. And this generalizes the classical homotopy groups when Q is a finite sigma model. So I can indeed define homotopy groups for non-invertible symmetries as long as I'm imposing these finiteness conditions. Now, if Q is a higher fusion category symmetry, so if this is described by a higher fusion category, then these two conditions, these finiteness conditions, they check, they match. So in particular, for a higher fusion category in these dimensions, I indeed get all of these homotopy groups. And there are examples of these higher fusion categories that are definitely counted as non-invertible symmetries. So even if I have a really non-invertible symmetry, I can still extract this list of groups. So there's still sort of classical invertible information. What's new now is the way these groups fit together. In the topological space, there's sort of a very constrained way how they fit together, and somehow for these non-invertible symmetries, we allow there's sort of more general ways how you can sort of put these groups together. Sort of the cohomology theory becomes different. And I should also say, the way we sort of write this and set this up, we can drop condition 1 and 2, and then things become more general. Also, we can drop the dimension. It doesn't have to be 4. We can also do something like this for 3-dimensional QFTs. But then what we see is that these won't be groups anymore. They won't instead be Hopf algebras or quantum groups. And in the d-dimensional case, they will be living in a braided category, not in a symmetric category. So originally, the title of this talk was Quantum Homotopy Groups. This is sort of the homotopy groups of quantum field theory. But I think a better title is Homotopy Quantum Groups, because, for example, in 3 dimensions, they give you actual quantum groups. Okay. So that's what I want to talk about. So let's get going. So first, what's the quantum fundamental groupoid? What is the fundamental groupoid of such? So let me sort of pick up one of these d-dimensional quantum spaces, and let's make the dimension d high enough. Then I can look at D-1. This will be a category now, right? This is the disk, and to the disk I assign this is I have a theory with boundary theory. I get a category, and this category is symmetric monoidal because I have this sort of pair of pairs multiplication that works in all dimensions. If I'm in dimension 3, this is actually just braided. In dimension 2, this is just monoidal. And just as an example, if I have a higher fusion symmetry, then this category is the category of Wilson line operators in the boundary theory. So it's the category of lines in the fusion N category. And this is symmetric if my boundary theory is high enough. And another example, I can go and compute this for my sigma model, and indeed it's just a category of representations of the fundamental groupoid. So this is how I want to sort of extract the fundamental groupoid. And now here comes the first kicker result by Deligne. Which implies, I mean, there's sort of a mathematical theorem, which implies that if Q is a compact and superlinear quantum space, then there actually exists a finite groupoid such that this category of line operators is just functors from this finite groupoid to supervector spaces. And this finite groupoid is the thing that I call the fundamental groupoid of my quantum theory. And I should say, now, if you just care about this sort of very finite case, that's good enough. I've already defined the fundamental groupoid. Let me say a little bit, if you sort of want to drop the finiteness conditions, then essentially the way you should think of this is that even without compactness, every symmetric category, C, can still be sort of, this comes essentially from algebraic geometry, where something you might be familiar with is that every commutative algebra you can think of as functions on some sort of weird, funny space. And similarly, you should think of every symmetric monoidal category as functors, as representations of some weird, funny, sort of fuzzy groupoid. Let me say maybe sort of some more words about this, because this will be useful later. In the case, if I have a rep of some groupoid, then the points in this groupoid are exactly the same as fiber functors, because I can just use the evaluation at this point, and then I go to vector spaces. And similarly, for such a thing, you can say, okay, there is an actual groupoid below it. I can just take the objects are the fiber functors, and the morphisms are the transformations between the fiber functors. But the point is just, there's sort of more data in the symmetric category. Sort of this is a groupoid, but there's sort of fuzz around it, like in algebraic geometry. So fine. And so I want you to think, even in this non-compact case, I want you to think of pi1 as being sort of this fuzzy groupoid underlying the symmetric category. Yes?
So for D equals to 4, the boundary theory can have Wilson lines which form braided fusion categories that are not symmetric?
For D equals to 4, the boundary theory will be 4-dimensional, and so it will be Wilson lines that are symmetric. For D equals to 3, it will be braided. That's right.
And in that case, how do you extract a group out of it? Because
so in that case, there is no group. That's just the thing that you have to. Then in that case, I'd still say, think of it as the groupoid, but there is no group. It's just a braided category. But in higher, you have this groupoid. Right. And the points of it are the fiber functors. Okay. So now I've talked about the fundamental groupoid. I think this is also sort of the ideas there are familiar to a lot of you. But let's talk about these higher homotopy groups. So classically, pi kx is an abelian group with an action by this fundamental groupoid, or rather for every point you get a group and an action. And mathematically, a way to say abelian group with an action is to say, this is the data of a commutative and co-commutative Hopf algebra inside the category of representations of the fundamental groupoid. So what we're really looking for is Hopf algebras in this category, in this disk category. And indeed, this is a theorem that these two data are equivalent. The abelian group with an action by this is the same as sort of a linear way to say this is that data. It's really equivalent data. You can classify commutative and co-commutative Hopf algebras as these. Okay. So now, to extract these groups, let's look at the solid torus. The solid torus, I just take it sk cross d minus k. So here are some examples. I can look at an annulus that counts as a solid torus, or an actual just solid torus, okay? Now we're doing the following. We're taking sort of, this is like a nice little donut, and I'm taking a bite out. So I'm just sort of going into the boundary and take a disk out. And now I can think of this as a bordism, as sort of an open-close bordism, a bordism with a boundary condition, from empty to the disk. So this would be a bordism from empty to a D2. This would be a bordism from empty to a D1. And so those give me objects in the category I assign to the disk. And it turns out, and this is the theorem, that these are Hopf algebras. These sphere cross disks, they will always be Hopf algebras in this category. Sort of roughly, I mean, this is sort of, it's tricky to build them, and you have to do some work, and there's sort of some, it relates back to ideas in lattice quantum information theory, I think, where we first came across this idea that something like this should work. But there is a multiplication, and roughly the multiplication is just you do the pair of pans on the sphere, and then there's a co-multiplication, which looks like you do a sort of pair of pans on the disk. And these are, of course, commutative and co-commutative if my dimensions are sort of, if it fits, like if the sphere and the disk are high enough dimensional. Okay. And now you can go in and compute this for these Dijkgraaf-Witten, for these finite sigma models. And the way you would do this computation, let me actually do it, because I can now do it on the board. You should think of this sphere. This is just SK cross D. It's just a thickened up version of the sphere. So if I want to talk about homotopy groups of a space, I just look at maps from the sphere into it, and maps from a sphere into some space. It's the same as maps from a sphere times a disk, because it's homotopy equivalent. And this byte, this is what forces a base point. So let's sort of just do it concretely. So let's look at, in the case of a finite sigma model, I said to the disk, I have rep of a groupoid. Let's understand what this Hopf algebra is, this QT. Well, it's rep of the groupoid, so understanding an object in this, I better sort of understand it one base point at a time. So for every base point of the groupoid, I do get a fiber functor. The way I can draw this fiber functor is, right, I was telling you should look at this guy. A fiber functor essentially is just something I can insert here labeled by x. So you can think of this as sort of a Dirichlet type boundary condition, where you force the value here to be x. And now what the theory is doing, it sort of looks at maps from the space to x, with the condition that at this point, they should take the value little x. And this is exactly what the fundamental group or what sort of these higher homotopy groups are. They're just maps from a sphere to my space that at a particular base point give you the value of this base point. So this is how you work out that what you see here is precisely the group algebras for the fundamental groups. And so then you go and define this pi k of q to be just Q of this Hopf algebra. The data of this is a commutative and co-commutative Hopf algebra in this category. And right, as I said before, if Q is compact and superlinear, this category is just rep of the fundamental groupoid. So you'll find here commutative and co-commutative algebra, Hopf algebra, in rep of the fundamental groupoid. But this is precisely the data of an abelian group with an action by pi 1. And so now we have extracted a fundamental groupoid and a bunch of abelian groups. And let me sort of say, right, the first thing, again, to remind you is this does not mean that the symmetry is invertible. There are actual non-invertible symmetries. You can still extract this data from it. And let me be very concrete. You can now ask, what is this pi kq in the case where you say have higher fusion symmetry? And I won't tell you this. I can tell you this in the break. But what I will tell you is this is not just an abelian group. It's an abelian group with an action by a group. And so the first thing you can ask for is, what is the quotient of this action? So what are the orbits? So take this abelian group and I just quotient by this group. That's a set. And this is precisely the set of k-dimensional defect operators in the boundary up to non-zero domain walls, or up to condensation. So this is something we care about a lot. We think of this as somehow the generalizations of the fusion ring in higher fusion categories. And this really always arises these cosets. So there's already something you learn, which is that the sort of generalized fusion rules, in some sense, of one of these higher fusion categories, if it's in high enough dimensions, will always be of a coset type. It will always be really given by an abelian group, quotiented by a finite group. And this is something we'll also see later in Julia Blavnik's talk, in the case of fusion 2 categories. Now this is in D equals 3, but still this phenomenon already appears there. There it will be a double coset rather than a single coset. Sort of in higher dimensions it turns into a single coset. Okay, so let me just sort of slowly get to an end of the talk. I've been almost a little bit quicker than I was allowed to, so yay. Let me get to the end, so then let me spend some time on the end of the talk. Let me say sort of a little bit how this, like why we cared about this question, how we sort of came to this question, and how we're using this question. So for us, the reason this came up is that we were studying S matrices. S matrices is the following. I have, for any one of these higher fusion categories, or for any one of these sort of generalized symmetries, I can look at an interesting pairing. It takes, essentially, if you think of this sort of roughly as being a k-dimensional operator, this is a d minus k-dimensional operator. I can pair these up by Hopf linking these k and d minus k operators in the boundary, and I can record the number I get out. So this is sort of a generalization of the S matrix you might know from modular fusion categories. This is like higher dimensional variance. So this is something we cared about and we wanted to study. Now here's something else. Let me sort of just drop this and let me say something else and then let me say how this relates. If I do care about groups, sort of groups only become interesting or groups only become useful once you know what once you know what an exact sequence is, long exact sequences. Long exact sequences are the things that allow you to compute with groups. Like to sort of build examples of groups, you need long exact sequences. And most long exact sequences come from the following so-called Puppe long exact sequence. If I have any map of classical spaces, I can have a sequence which goes pi kx, pi ky, then have pi k of the fiber, or really the homotopy fiber of f, and so on, and so continues like this. And we do have a generalization of this long exact sequence to quantum spaces. So we have to sort of say exactly, as I've told you what a quantum space is, I haven't yet told you what a map of quantum spaces is. This will sort of involve a bulk theory and two boundary theories and an intersection between the two boundary theories. But then there is sort of a long exact sequence you can extract from it, which in high enough dimensions and for finite enough theories gives you actual long exact sequences of these groups, and you can start computing them. And it turns out that this S matrix pairing appears as a connecting map in this long exact sequence. And you can use this, and this is what we originally wanted to use this for, to prove the following theorem, that if I take such a quantum space, then the bulk theory is invertible. So this is something we know well in 3 dimensions, or in 2 dimensions for modular fusion categories. If the bulk theory is invertible, this is equivalent to the statement, and this is like a complicated categorical thing, right? This is like, there's like lots of information contained in saying that the bulk theory is invertible theory. But this is equivalent to something very, very low dimensional, just sort of a question about matrices. Namely the statement that all of these matrices for all k are non-degenerate. And it is quite surprising. We know it in examples, but it is surprising. This is really just something about the boundary theory. It's just something about boundary operators, and it's something about numbers, right? And this is something about sort of higher dimensional complicated stuff. And these are equivalents. In other words, boundary operators operate non-degenerately. That's what we use. And this just follows from this long exact sequence here, because the S matrix will just be a morphism. And if the morphism is invertible, then the other term will be trivial. And the other term sort of tells me about operators in the bulk theory. Essentially, that's how it goes. And this leads to a bunch of cool stuff, like Berliner formulas in higher modular fusion categories, which relate fusion coefficients and braidings. Already in these higher dimensions, this is not necessarily a square matrix. K doesn't need to be equal to D minus K, so this tells you that you can learn something about K-dimensional operators if you understand D minus K-dimensional operators, which is also very useful because usually the sort of lower dimensional operators are easier to understand than the higher dimensional ones. So you learn all sorts of things about these symmetries from that statement. Right, but sort of at the heart of it is this idea that these things are really groups or Hopf algebras in lower dimensions. Right, and so that's the end of my talk. Thank you for your attention.
So for 2 dimension, you mentioned that you construct Hopf algebra. Is Hopf algebra or weak Hopf algebra?
So in 2 dimensions, I don't do anything. In 3 dimensions, so this is the dimension where your boundary operator of fusion 2 category, I do get Hopf algebras in a braided monoidal category. In 2 dimensions, this is just a monoidal category. I think you can do something analogous and you get these Hopf monads, I'd say. But you don't get Hopf algebras in a braided category in 2 dimensions. That's right. But I mean, this only, like what we're doing only applies to 3 dimensions and higher. And it really only gives these groups in 4 dimensions and higher.
So I was wondering about this long exact sequence you had at the end. So, yes. Right, so classically, there's like this adjunction thing that you get that long exact sequence with. What's the analog for the quantum case? What's this adjunction?
How do you get this long exact sequence?
Yeah, I mean, like the classical thing is like there's this tensor hom, you trade the arguments for the output, kind of stuff to get long exact sequences. What's the equivalent for the quantum case?
I mean, in a way, the only thing I can tell you is that the sort of thing that replaces now a map of spaces is a space is a bulk theory with a boundary theory. And then a map of spaces, the way we want to think of it, is a bulk theory with 2 boundary theories and a morphism between the 2 boundaries, sort of a corner between the 2 boundary theories. And then you can just go and write down the analogous, and you can sort of form a map of spaces. You get such a configuration in sort of a finite sigma model way. And you can actually go and just write down exactly all of these groups you can write down in terms of sort of products and spheres and disks with some interesting stratification using like the spike theory, these two boundary theories and so on. So you just sort of in a way do it by hand. But also before we're doing it by hand, somehow all of these, we can't do really fancy arguments with it because the thing that we are looking at is a TQFT with a boundary theory. They don't, like that's what they assemble into, so you have to say it in terms of TQFTs. There's just, you have these groups, but the way they assemble is just as a TQFT.
Thank you.
David, is it possible to sort of assemble these homotopy groups and use it as sort of like a generalized twisted cohomology theory, or maybe how does it fit into sort of a connective spectra, I guess?
That's what I'd imagine that you could sort of, the next question you could sort of very sensibly ask is, okay, now I have these homotopy groups, what else is there? What else is in a quantum space? Like, can I use this as a starting point for sort of collecting data that assemble into a quantum space? And for topological spaces, we know, like you could ask the same question, and what there is sort of this K invariance, these sort of various extension data that you need, and these are captured by cohomology theory. Like that's what it is. It's like just cohomology theory, and in the end it's just cohomology theory of Eilenberg-MacLane spaces of K and of like R-form symmetries. And so now you'd expect something similar, but the cohomology theories that you'd use would be more complicated, and they would sort of depend on, and you notice in a bunch of examples, they would depend on sort of extension theory. So they would know, like the cohomology theories that you'd use, they would know about interesting sort of modular categories and higher versions of it. So there's like all the quantumness is in the connecting information. But I think you can phrase it in terms of cohomology theory with interesting targets, with interesting spectra, with sort of very exotic cohomology.
But would the spectra only be kind of finite at the top? Because you're using like a finite dimensional theory.
Yeah, you would, I mean, for a d-dimensional thing, it would just go to some, you just need to consider it in some levels. Yeah.
Okay, thank you.
Yeah, I wonder whether your results can be framed as follows. You might have a fusion category, fusion higher category, which is a symmetry. Their bulk is some kind of a higher gauge theory, which is related to some kind of non-linear sigma model. Is that a right way to understand your results, or your result imply something along that direction?
So I think it's not strictly necessary that the bulk theories need to be higher gauge theories. I think you can loosen the notion of higher gauge theories so far that you can make it be one, but I think there are examples of things where the bulk is at least not a sort of higher gauge theory just for a finite group. So you at least need to have higher form groups to say this. So I think this is not necessarily contained in these results. So I think what you were saying would be stronger than these results. But these results are still are these finite groups you can extract. But I think already in the bulk, you can have interesting ways how they fit together, which aren't just given by a
So certainly higher gauge theory, we assume they can have this co-cycle twist, so twist higher gauge theory. But you say that what you describe here is beyond the higher gauge theory. But in which sense? In higher gauge theory, on every level there's a pi 1, pi 2, pi 3.
That's right.
There's some it's groupoid.
Yes.
So in your case, that's beyond groupoid.
That's right. It should go beyond groupoids. It is just some higher category.
Okay.
But somehow you still can extract this group. So it's like it's not as far away from a groupoid than the generic category.
I see. Okay. Yeah. Thank you.
It's somehow a category which feels very close to a groupoid.
Is there a way to distinguish using these quantum homotopy groups whether the symmetry, I think Q you called it, is sort of just like group-like or is not group-like?
That's a great question. That is I think it's a great question.
Four dimensions, physicists would care about is it a one-form symmetry, zero-form symmetry, or actually it's like a duality symmetry?
That's right. So if you just look at the groups, of course you can't, like all possible choices of groups, you can sort of build a space which has these groups. But so, for example, if you start looking at things like the S pairing, there's sort of, the idea should be there's more data on these groups, and the question is, what additional data do you want to do you have to say at the top of that?
So it's not detectable just from these.
I think it's not detectable just from the groups, just because I can really build any space with any homotopy groups. But I do agree that there's you could ask what's the minimal additional amount of data, very finite data to detect it, and that's interesting.
So my question is about quotienting by the condensation defects that you mentioned.
So can you repeat the question?
Like quotienting by condensation defects, like the full set of defects and quotiented by condensations. So if I think about the case of 3+1D TQFTs, where I have some surface operators,
yes.
Some of them are condensation, some of them are not.
Yes.
If I quotient the set of surfaces by condensation,
yes.
do I get something group-like always?
That's right. So what you get is, this is exactly right. So what you get is, so you get, say, look at the surface operators in your 3+1D QFT, and you quotient by two things being the same if there is a just domain wall between them, which is non-zero. And then what you can extract from this is the abelian group quotiented by the action of the fundamental group. So an example is, if, say, your fundamental group is trivial, this means that your category has no lines. Suppose you have no lines in a boundary theory. No lines in a boundary theory, these are the simply connected QFTs somehow in this language. And then this just becomes pi k. Then you can compute the abelian group pi k as the surface, like pi 2 in this case, would be the surfaces up to condensation. And then you indeed would have a group structure on fusing these surfaces. Okay. It would indeed be this abelian group that tells you this fusion. And in general, I think what this tells you is that there is this coset, and on the coset you have a multiplication, but this multiplication is not a group, it's sort of like a fusion ring type thing, and this sort of gives you a very coarse-grained way of telling you how fusing these surfaces would work.
So you cannot have non-invertible surfaces unless you have some condensation surfaces somewhere in the system, right? Because...
so this would...
Because you can always, I guess you're saying that in general, if you quotient by condensation, you always get something group-like. So
no, it's still like there are examples of completely non-invertible symmetries where you can still extract, being able to extract these groups doesn't mean that the symmetry is non-invertible. Like there can be symmetries that are completely still non-invertible, but yet even in a simply connected case, even if you assume that this guy is trivial, then the fusion of these surfaces, it behaves group-like. And it sort of behaves group-like at all levels up to condensation, but not if you don't do it up to condensation. Like the interesting thing is like what's the actual fusion of the surfaces? Up to condensation, it will be like they'll fuse together as group elements, but not sort of if you go away.
Thank you.
Hi, David. Thanks for the nice talk. I have a naive question about the end slide about the applications. You mentioned this hop link, and it's used to induce some sort of generalized Berlin formula. In studying symmetry TFTs for higher dimensional field theory, we find that this was known also in the condensed matter literature, that oftentimes you can go beyond the hop link. There are like higher link invariants, Brownian links, Borromean rings, and they can lead to further terms that are relevant in physics application. Do you see they have a counterpart in the formalism, like as a...
So here the point is that this is, I think, the only one. Like again, let's do sort of the simply connected ones. The point is that these hop links are the only ones that do descend to the quotient up to condensation. Like that's sort of the idea. Like these higher things, they do depend on the actual surface you're using or the actual manifold you're using, not just up to condensation. Like if you have a boundary which isn't invertible, you can't switch the value of these higher things. But for spheres it works, because if you take a sphere, you sort of punch your circle into it, and then you sort of wrap the circle around and cancel it. That's the idea. So this is the only hop-link pairing that descends to things up to condensation. And this is the one which is, it suffices to just consider these, and only sort of on these quotient groups, to detect invertibility of the bulk theory, to detect that there's no operator in the bulk. Like that suffices. That's right. Like the ones that you're telling, this definitely tells you finer information, but it tells you sort of information that goes far beyond the homotopy groups. Like somehow you can't even say it in terms of data on top of the homotopy groups.
Thank you.
Let's thank the speaker once again.